Hello students, welcome to EPG Parsala. I am Dr. Devrat Mishra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Optical Properties 7 from paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. So we will see the luminescence property of a material, then we will learn what is excitation and emission phenomena. Then I will talk about the Franck-Condon principle of the transition in material, concentration and temperature dependence of luminescence efficiency would be described, and electroluminescence property of a material will also be explained. Luminescence: when a substance absorbs energy in some form or the other, a fraction of the absorbed energy may be re-emitted in the form of electromagnetic radiation in the visible or near visible region of the spectrum. This phenomenon is called luminescence, with the understanding that this term does not include the emission of black body radiation, which obeys the laws of Kirchhoff and Wien. Luminescent solids are usually referred to as phosphors. Luminescence is a process which involves at least two steps: the excitation of the electron system of the solid and the subsequent emission of photons. These steps may or may not be separated by intermediate processes. Excitation may be achieved by bombardment with photons, which is photoluminescence, or with electrons, which is called cathode luminescence, or with other particles. Luminescence can also be induced as the result of a chemical reaction, which is called chemiluminescence, or by the application of an electric field called electroluminescence. Luminescence is that frequently the ability of a material to exhibit luminescence is associated with the presence of activators. These activators may be the impurity atoms occurring in relatively small concentration in the host material, or a small stoichiometric excess of one of the constituents of the material. In the latter case, one speaks of self-activation. The presence of a certain type of impurity may also inhibit the luminescence of other centers, in which case the former are referred to as killers. A number of important groups of luminescent crystalline solids may be mentioned here. Number 1. Compounds which luminesce in the pure state. According to the Randall, such compounds should contain one ion or ion group per unit cell with an incompletely filled shell of electrons, which is well screened from its surroundings. Examples are probably the halides, samarium and gadolinium sulfate, molybdates and platinocyanides. Second, the alkali halides activated with thallium or other heavy metals. Third, zinc sulfide and cadmium sulfide activated with copper, silver, gold, manganese, or with an excess of one of their constituents. Fourth, the silicate phosphors such as zinc orthosilicates activated with divalent manganese, which is used as oscilloscope screens. Oxide phosphors such as self-activated zinc oxide and Al2O3 activated with transition metals. Organic crystals such as anthracene activated with naphthalene. These materials are often used as scintillation counters. Excitation and emission. Let us assume that the luminescence is associated with the presence of activator atoms. The incorporation of an activator atom in a crystalline solid will in generally give rise to localized energy levels in the normally forbidden energy gaps. These localized levels may be classified into two categories. Number 1, levels which belong to the activator atoms themselves, and second, levels belonging to host atoms which are under the perturbing influence of the activators. The levels of group 2 may be associated with host atoms in the immediate vicinity of the impurity atoms, but they may also be associated with lattice defects, for example vacancies, whose existence is tied up with the incorporation of the activator. For example, if manganese 4 plus ions were incorporated on sites normally occupied by zinc 2 plus in a zinc sulfide lattice, there may be localized levels associated with the Mn 4 plus ion, levels associated with the S2 minus and Z zinc 2 plus ions in the vicinity of the manganese 4 plus ion, and levels associated with ions in the vicinity of a positive ion vacancy produced as a result of the presence of the Mn4 plus ion to compensate for the excess positive charge. In terms of the energy band pictures of figure 1, let G and A be two levels corresponding to one of the categories 1 and 2 mentioned above. In the ground state, level G is occupied by an electron and A is empty. In the excited state, the reverse is true. The excitation from G to A may be accomplished in at least three ways. A. It is possible that an incident photon of the proper frequency is absorbed directly by the electron in level G, whereupon it arrives A, say figure 1a. As a result of lattice vibrations, this absorption will correspond to a band centering about a certain frequency μa. The excitation process may also involve the diffusion of an exciton. Suppose, for example, that in some part of the crystal an exciton is produced. Since the exciton may diffuse about in the crystal, it may reach a center such as Ag, whereupon it may give off its energy to the center, resulting in excitation of the electron. This consideration is of importance since it provides a mechanism whereby energy can be transferred from the exciting source to the impurities via the host crystal. In other words, the exciton mechanism make it possible for the activators to receive more energy than they ought to be on the basis of their relative concentration in the lattice. Figure 1 shows the ground state G and an excited state of the luminescence center. In A, excitation takes place by direct absorption of a photon. In B, excitation is achieved by a capture of a hole at G end of an electron at A. C. The excitation process may also involve the motion of free electrons and holes. For example, let electron-hole pairs be created somewhere in the crystal, as for example by bombardment with photons or electrons. If the center Ag is in its ground state, the level G may capture a hole from the valence band and A may trap an electron from the conduction band. In this way, excitation of the center has been achieved, as indicated in figure 1b. Evidently, this type of excitation process should be associated with conductivity, in contrast with processes A and B. The Franck-Condon Principle. From the simple energy level diagram of figure 1, one might get the impression that the return of the electron from the excited state A to the ground state G should be accompanied by emission of a photon of a frequency equal to the absorption frequency. This is not the case since the Franck-Condon principle must be taken into account. In figure 2, we have represented the levels A and G as function of a configurational coordinate q. Each value of q corresponds to a particular configuration of the nuclei in the vicinity of the luminescence center. During the optical excitation from G to A, the nuclei remain essentially at rest, leading to an absorption energy. After the absorption act, the nuclei do not occupy the equilibrium position proper for the excited state, and the system will move gradually to the minimum of the A curve with emission of phonons.
This process is possible since the lifetime of the excited state is 10 to the power minus 8 second as compared with periods of the order of 10 to the power minus 13 second associated with lattice vibrations. The emission act itself, like the absorption act, takes place vertically in figure 2a so that nu is less than nu a. Thus, luminescence centers are in general transparent or nearly so with respect to their own emission bands. Figure 2 represents energy of the ground state G and of an excited state A as function of the configurational coordinate Q. The situation A gives luminescence, B gives corresponds to dissipation in the form of heat.
Radiationless transitions. An excited center in a crystal can return to the ground state either with or without the emission of a photon. A model corresponding to the former case is the one represented in figure 2a. For non-luminescent materials, she has suggested a model in which the return to the ground state of an excited center can take place by means of a radiationless transitions. Thus, in figure 2b, the system may move after the absorption act from A to A prime and then cross the narrow gap to point G prime associated with the ground state, perhaps with emission of a low frequency photon. In this way, the energy of the absorbed photon Ga is essentially transferred into heat, that is, into vibrational energy.
Temperature dependence of luminescence. With reference to figure 2a, we note that the excited center might also return to the ground state by means of a radiation-less transition via the routes A double prime, G double prime, G. Such a model has been suggested by Mott and Gurney to explain the observed decrease in the luminescence efficiency of phosphors at high temperatures. When Pe represents the probability per second for an excited center to return to the ground state with photon emission, and Ph represents the probability for energy dissipation in the form of heat, the luminescence efficiency eta may be defined as eta is equal to Pe by Pe plus Ph, which is equal to 1 plus Pe by Ph whole inverse. Since it seems reasonable to assume that Pe is nearly temperature independent, pH must be mainly responsible for the temperature effect. For a model such as in figure 2a, the probability pH is determined by the probability to find the excited state in a vibrational level corresponding to A double prime or higher. One may then write pH is equal to nu into exponential of minus E by kT, where epsilon is the energy difference between A double prime and A prime and nu is the frequency. Thus, for this model, pH increases as T increases and the efficiency decreases. Concentration dependence of the luminescence efficiency. If one defines the luminescence efficiency eta as the number of emitted photons per incident photon absorbed by the material, one obtains experimentally for many luminescent materials a curve for eta versus atomic activator concentration C, which exhibits a maximum for a certain activator concentration. For the particular case in which the excitation of the luminescence center is achieved by the direct absorption of a photon, such as in the thallium activated alkali halides, the efficiency versus concentration curve may be interpreted on the basis of a simple model. Suppose that an activator atom which has absorbed an incident photon returns to the ground state with emission of a photon only, if there is no other activator atom within a sphere of radius r around the central activator atom. In other words, we assume that the activator atoms interact with each other in such a way that if the distance between them is very less than capital R, they quench each other. Thus, around a given Ti plus ion, let there be Z metallic positions within the sphere of radius r. If any of these Z positions is occupied by another T1 plus ion, we assume that neither of them will act as a luminescence center. due to the quenching effect, then eta will be proportional to C into 1 minus C whole to the power Z, where in figure 3 schematic representation of the luminescence efficiency as a function of activator concentration. C represents the probability that a given metallic site is occupied by a T1 plus ion. Furthermore, eta will be proportional to the probability that a photon absorbed by the material as a whole is actually absorbed by a T1 plus ion. This probability is given by an expression of the type alpha C divided by alpha C plus beta into 1 minus C is equal to C by C plus beta by alpha into 1 minus C, where beta by alpha is the ratio of the capture cross section of a photon of a given wavelength by a lattice atom and by a T1 plus ion. Evidently, the ratio beta by alpha will be a function of the wavelength of the exciting radiation. It also depends on temperature. Thus, eta is equal to C into 1 minus C to the power Z whole divided by C plus beta by alpha into 1 minus C. For small concentrations of the activator, eta increases proportionally with C. At high concentration, the mutual quenching takes over, leading to a decrease in eta.
Electroluminescence. The term electroluminescence covers a variety of phenomena which can occur when a luminescent material is subjected to an electric field, and some of these will be discussed below. The Gordon-Pohl effect. In 1920, Gordon and Pohl discovered that a momentary flash of light is emitted when an electric field is applied to a zinc sulfide phosphor during the afterglow, that is phosphorescence. When a DC field is applied, a flash is observed. The same is true when the field is switched off. This indicates that after application of the field, an internal field is set off due to polarization, which rapidly counteracts the external field. When the latter is removed, the polarization field itself produces a flash and decays rapidly to zero. The momentary flash may also be observed when the field is applied during excitation with photons. Luminescence associated with the application of a field during or after photoexcitation is referred to as electrophotoluminescence. The Gordon-Pohl effect is evidently due to the emptying of electron traps. This may occur as a result of tunneling of electrons from the traps into the conduction band, or it may be due to ionization of the field traps by free electrons accelerated by the field in the conduction band. In any event, the effect is somewhat analogous to thermoluminescence, the action of the field taking the place of the action of thermal vibrations.
The Destroyer effect. The emission of light by a phosphor resulting solely from the activation action of an electric field applied to a suspension of luminescent particles in an insulator was first discovered by Destroyer. In this case, one may speak of intrinsic electroluminescence, since the effect does not involve previous photoexcitation, nor the injection of charge carriers from an external source. An electroluminescent cell is usually made in the form of a parallel plate capacitor, of which at least one of the conducting plates is transparent. In order to transfer power to the dielectric consisting of the luminescent powder embedded in an insulator, alternating voltages or pulses must be used. For sinusoidal voltages, the average brightness B increases rapidly with increasing amplitude. Several empirical formulas have been introduced to describe the observed brightness versus voltage curves. For example, B is equal to A into V to the power n into exponential of minus B by V, where A, B and C are constants. The curve shown in figure 4 has been obtained by robots for a copper activated zinc sulfoselenide phosphor embedded as a powder in a variety of dielectric materials. If one assumes that the luminescent particles are sphere, one can show that the local field E2 in the phosphor is given by the expression E2 is equal to 3 epsilon 1 into E, capital E, divided by 2 epsilon 1 plus epsilon 2 minus F1 into epsilon 2 minus epsilon 1, where E is the applied field. Epsilon 1 is the dielectric constant of the phosphor, epsilon 2 is the dielectric constant of the matrix, and F1 is the fraction of the volume occupied by the phosphor particles. By using various matrices of widely different dielectric constants, Roberts showed that observed brightness is a function only of the local field E2. The brightness varies only slightly with temperature, indicating that thermal excitation is of little importance in the mechanism. Electroluminescence becomes visible for fields above 3000 volts per centimeter. For high brightness, one requires fields approximately 10 times as strong. A possible explanation of intrinsic electroluminescence presumably involves the emptying of traps by the field, subsequent acceleration of electrons in the conduction band, and excitation of centers by these electrons. Piper and Williams have studied the electroluminescence of single crystal zinc sulfide copper clamped between two electrodes. From the non-ohmic behavior of this system, they conclude that there exists a Schottky barrier at the crystal metal interface with an applied electric external field. The local field in the barrier may well be of the order of 10 to the power 6 to 10 to the power 7 volts per centimeter. Although such fields are appreciably larger than the breakdown field of insulators of the order of 10 to the power 4 volts per centimeter, breakdown does not occur because the Schottky layer is thin of the order of 10 to the power minus 5 centimeter. When electrons in the Schottky layer are accelerated by the field, they may produce luminescence by impact with luminescence centers.
Carrier injection luminescence. When a p-n junction of germanium or silicon is biased in the forward direction, electrons from the n region penetrate into the p region and holes flow from p to n. The minority carriers so injected will recombine with their counterparts, and one might expect emission of photons. This has indeed been observed by ions and bricks. The emitted radiation has a wavelength which agrees well with the optical absorption associated with band-to-band transitions. For germanium and silicon, the radiation lies in the infrared, lambda is equal to 1.77 mu micron to 1.22 micron respectively. The emission is localized in the junction region. So students, let us summarize what we have learnt in this module. Luminescence property of a material and excitation phenomena are also explained. Luminescence efficiency dependence on temperature and concentration was described. We saw the electroluminescence property of a material and its effect. Franck-Condon principle of the radiation transition is also explained. Thank you.